Hello everyone, my name is CJ from Carnegie Mellon University. This presentation is about our work, the behavioral notion of robustness for software systems. Other authors are Garlan and Eunsuk Kang from Carnegie Mellon. According to IEEE, robustness is the degree to which a system or component can function correctly in the presence of invalid inputs or stressful environment conditions. Just like other quality attributes, we are interested in how to measure robustness and how we can improve the robustness of a system. Existing techniques regarding robustness focus more on testing. For example, fuzzing testing and chaos engineering can be used to approximate the robustness of a system. Often they use system not crashing as a standard of correctness. Then they use randomized inputs or fault injection to try to make a system crash. Finally, they use error rate to measure the robustness. However, error rate is not a direct metric to robustness, and more importantly, it is not applicable to design phase. However, for safety-critical or mission-critical systems, it is important to ensure that the design can guarantee some level of robustness. If we look into other disciplines, they do have methods which focus on ensuring the system robustness at design phase. For example, in aircraft engineering or civil engineering, we cannot afford we build a bridge first and then test whether it is robust or not. However, in software engineering, such method seems to be missing. We also need a way that can achieve robust by design, especially for those safety-critical or mission-critical systems. For robust by design, we are proposing a development process where developers first come up with an initial design. Then they use a tool to analyze the robustness of that design. Then, with the analysis report, developers can decide whether the design meets the desired level of robustness. If not, they can do another iteration to improve the design. Or if it does, they can go and implement the system. Therefore, the main contributions of this work are: we first provide a formal definition of robustness. Then, we present a technique for computing and representing robustness according to our definition. Then, we demonstrate that our tool supports the proposed robust by design development process. In this work, we use label translation systems to model the behaviors of a system and its environment. LTS is a simple notion to model behavior as sequences of actions. In our context, a system should ensure a safety property. That is, intuitively, the system should not have bad behaviors. Then in general, a system is robust if it is capable of ensuring a safety property under environmental behaviors that deviate from the norm. To better illustrate this idea, we use the infamous Theoric 25 system as a running example. Theoric 25 is a radiation therapy system which caused a few deaths. A comprehensive defects analysis has been done, and it is quite complex. Thus, in this talk, we will use a simplified version and focus only on risk condition error. For label translation systems, basically we model systems or environments as state machines. For Theoric 25, it has three components. A model defines its user interface. A model defines the switching of radiation modes. Theoric 25 has an X-ray mode and an electron beam mode. And a model defines the switching of a spreader, which is using X-ray mode to reduce the power level to avoid overdose. For the interface model, it defines how a user can interact with the system. A typical use case is the user selects either X-ray mode or electron beam mode, then confirm the mode, finally fire the beam. Also, the user can use up to back to the previous step. For the mode switcher, there is a non-neglectable delay when the user is switching from one mode to the other. For example, if the system is in X-ray mode, if the user switches to the E-beam mode, then the system will still be in X-ray mode until the set action has happened. And we will see that this delay may cause overdose or underdose problems. A spreader is used in X-ray mode to avoid overdose. The table shows the possible combinations of the states of the spreader and the radiation modes. In particular, X-ray combined with the spreader out of place will cause overdose, and E-beam mode combined with the spreader in place will cause underdose. In this example, the environment is the behavior model of a user. Here we assume the very basic use cases of the system. That is, the user chooses either X-ray or E-beam mode, and then confirm and fire. Under this operation model, we can use existing techniques such as model checking to verify that no overdose nor underdose will happen. However, a system is safe under the typical use cases does not mean it is robust. What if the operator makes a mistake? In fact, the system is not robust. A known overdose case is the user selects X-ray mode, but then changes to E-beam mode. At this time, the spreader goes out of place, but the system is still in X-ray mode. Then, before the mode switch is complete, the user confirms and fires, which causes overdose. Thus, we say the system is not robust against this deviation. On the other hand, it implies that a more robust system should be able to handle more deviations compared to the initially expected environment. Based on this intuition, we'll provide a more formal definition of robustness. To understand our definition, let's say we have a system model M, which is 325, an environment model E, which is the operator, and the safety property, which is no overdose. Then alpha I is the set of interface actions. They are X-ray, E-beam, confirm, up, and fire. Alpha I star represents all the possible traces over alpha I. The first circle describes all the environmental behaviors allowed by the machine. The traces could be infinite. Here we pick the most critical ones. They are the user chooses X-ray or E-beam mode, and then confirm and fire. Or the user chooses X-ray mode or E-beam mode, but then changes to the other mode, and then confirm and fire. The inner small circle describes the behaviors defined by the environment model, which capture the expected behaviors of the environment. Here we have the user chooses X-ray or E-beam mode, and then confirm and fire. As we know, under this environment, the property that no overdose is satisfied. Then, the gray area is the subset of behavior that may or may not satisfy the property. Here we have the user chooses X-ray or E-beam mode, but then changes to the other mode and then confirm and fire. We can further break it into two parts. The red area describes the subset that violates a property. As we've discussed, switching from X-ray mode to E-beam mode may cause overdose. The circle in the middle is the largest subset of system behaviors that still satisfy the property, which we call the wicked assumption of the system. When we design a system, it is often hard and almost impossible to make it work under any environment. Thus, we make assumptions about the environment and try to make sure that the system should work under these assumptions. Thus, an assumption is weaker means the system is making fewer assumptions about the environment. That is, the system should have more behaviors satisfying the property. Thus, the wicked assumption is the largest subset of environmental behaviors under which the system still satisfies the property. Then, if we compute the difference between the wicked assumption and the given environment, we can get a set of deviations under which the system satisfies the property, but is not defined in the given environment. For example, in this case, we have the user chooses E-beam mode first and then switches to X-ray mode. We know that this is not defined in the original operation model, but will not cause overdose, even though it may cause underdose. In sum, more formally speaking, we measure robustness as the largest set of deviations of the environment under which the system can still satisfy the safety property, which is represented as the blue area in the diagram. With this definition, we can formally compute robustness, traditionally, by giving a system model and an environment model and a safety property. A verification tool like a model checker can only tell the property is satisfied or violated by a counterexample. But now, our tool can compute the deviations under which the system is robust compared to the given environment with respect to the property. We can also compare the robustness of two designs by giving two system models, M1 and M2. We can compute the deviations under which M1 is robust, but M2 is not, and vice versa. Also, we can compare the robustness of one design under two properties. For instance, one is stronger and one is weaker. We can compute the deviations under which M satisfies property 1 but not property 2, and vice versa. To compute robustness, we first use the existing approach to compute the wicked assumption of a system with respect to a safety property. Then we compute the difference between the wicked assumption and the given environment. However, there are two problems. First, the difference is a set of infinite number of traces. It is not possible for developers to go through these traces to tell how robust their system is. We need a way to extract valuable information from this infinite set of traces. Second, the trace is under the alphabet of the interface. Developers cannot tell what are the errors which cause the deviation. For example, what mistakes of the operator can result in a trace like E-beam, up, X-ray, confirm, and fire. We believe that knowing such a trace over the alphabet of the interface is not enough. Developers are more interested in what are the errors the system is robust against. For the first problem, we group the traces into a finite number of equivalence classes. For example, take E-beam confirm fire as a reference trace. We can create a class of deviations E-beam up, which represents all the deviation traces that start with E-beam up. So each class is a comma prefix to a set of deviations, and that prefix ends with the first deviation action. There are different ways to group the deviation traces. Here we choose to focus only on the first deviation action. For example, up is the first deviate action compared to the reference trace. Our rationale is that even if we have a trace with multiple errors, since the behavior already deviates from the expected one, so it may not be important to focus on the rest errors, which might be infinite. For the second problem, we introduce a deviation model to generate explanations for the representative traces. We think such explanations can help developers understand what errors the system is robust against. In short, a deviation model is an environment model with error transitions. For example, in the deviation model for 3025, we add a commission transition from confirm mode state to select mode state. A commission error means the user does something that should not be done. That is, instead of doing confirm, the user does up action. Thus, we can generate an explanation for the representative trace. That is, the user chooses E-beam mode and performs up because of a commission error. And we can conclude that the system is robust against this scenario. A deviation model can be manually created by a developer or can be automatically generated from an existing model from another domain. For example, in our case study of 3025, the environment is the behavior of the operator. In HCI study, they have this tool called Enhanced Operator Function Model, EOFM, to model a task for an operator. We won't go into details about it, but researchers have developed a technique to generate human mistakes with this task model. Thus, we automatically generate our deviation model from this existing technique. The advantage of doing this is that developers are not always the expert in the corresponding domain. They could rely on input from other domain experts, and developers together with the domain experts can tell what environmental errors the system is robust against. To summarize the computation process, first, by giving the model of the machine, the environment, and the safety property, we use an existing technique to compute the weighted assumption of the system. Then we compute the difference between the weighted assumption and the given environment to get a model of robustness. With this model, we generate equivalence classes and representative traces for representing robustness. Finally, we introduce a deviation model, which is an environmental model with error actions, to provide explanations for the representative traces. We conduct 2 case studies to evaluate our approach. In particular, we like to demonstrate that our tool for computing robustness is useful and it can be applied to different domains. In the first case study, we compare the robustness of a new design of 3025 to the original design. Our tool shows that the overdose scenario is now addressed by the new design, where we add a safety check before firing. Then we compare the robustness of the old design under 2 properties. One is that there should be no overdose. Another is that there should be no overdose and no underdose, which is a stronger property. Our tool shows that robustness is lower under the stronger property. In the second case study, we analyze the robustness of 2 network protocols. One is the protocol assuming a perfect channel, another is the alternate bit protocol, which is a simple protocol designed for unstable channels. Our tool shows that the alternate bit protocol is more robust in the sense that it can handle message loss, message duplication, and limited support for message corruption. More than that, we find 8 scenarios where our deviation model cannot find explanations, which means that the protocol is even more robust than we previously believed. More details can be found in the paper. To review the robust by design process we are proposing, developers may often start with a design which satisfies the functional requirement under the typical environment. At the same time, a group of domain experts may analyze the potential faults in the environment and create a deviation model. Then they can use our robustness analyzer to compute the deviations and their explanations that the system is robust against. In one case, the domain experts may find that some critical scenarios are missing, and the developers can work on fixing that, which improve the robustness of the system. In another case, the domain experts may find that some unlikely scenarios are covered by the system, but on the other hand, may introduce overhead. This often happens in the case that developers are over-engineering the system. Then the project manager may jump in and emphasize that we could simplify the system to remove some checks to meet the schedule and budget. Finally, they may find some scenarios are not covered but with low risk. Fixing all these defects may introduce overhead or cause the project to delay or run out of budget. Then the team may decide to leave them as technical debts and continue to implementation phase. In sum, there are many more use scenarios. Compared to traditional model checking tools, our tool provides a systematic view of system robustness at design time. That is, what erroneous scenarios are covered and what are not. With this information, developing teams can make more reasonable decisions regarding the robustness or overall quality of the final product. In the future, we'd like to work on robustness computation for non-safety properties, for example, liveness properties. Also, we're interested in how to synthesize a new design of a system which improves its robustness. For example, by using some model repair or model transformation techniques, we can get a new design M prime such that M prime is more robust with respect to the environment E and property P. To conclude, in this work, we are promoting a robust by design process for software development. We propose a formal definition of robustness and present a technique for computing it. And we demonstrate that this tool enables a robust by design process. This is the end of the talk. Thank you for listening.